Okay, we are back. So much drama. All right, that was a good point to stop. What have we done so far? It's been over an hour. We've looked at, maybe less than an hour, we've looked at the historical attempt to describe natural languages with grammars, specifically generative grammars. We talked about how generative grammars are important for computer science applications, and we now have moved towards looking at this more formally, and we've introduced what a grammar is, and lots of notation and lots of vocabulary, and we've seen an example of a grammar and a finite state automaton that recognizes that same language. Okay, it's finally time to get to a specific kind of grammars that we're going to talk about today. And the specific kind of grammars that we're going to talk about are regular grammars. Okay, so what is a regular grammar? This is related to everything we've been doing so far, but now with some additional restrictions. Okay, so like before, a regular grammar has an alphabet, which is a finite set of characters, or symbols. We have a set of non-terminal symbols. Okay, and Gossett, this is where Gossett essentially starts his lesson, but I think now we have a very good intuitive sense of what a non-terminal symbol is. They're the sort of the theoretical symbols that we've sort of created to aid us in expressing the grammar. Whereas the alphabet is the set of well, I'll get to that in a second. There's a start symbol, which is just S, and then there's a set of production rules. And Gossett is going to use this phrase terminal symbols, and the terminal symbols include everything in the alphabet, but also we reserve the right to use this symbol, the symbol for the empty string, is also one of our terminal symbols. Okay, we have all these rules, and the definition of grammar is general enough to include a whole bunch of different kinds of grammars, but specifically what makes a grammar regular is that its rules are of a very particular kind of restricted form. And so in a regular grammar, every single rule is going to look like this. It's of the form n goes to v, where n is a non-terminal symbol. So that means that we are going to always be replacing a single non-terminal symbol with some other stuff. Every grammar we've seen so far does that, but you could imagine, if you're being very creative, more complicated production rules that also, say, replace some terminal symbols, so some characters are deleted or something like that. We're not going to talk about that in this class, basically. So on the left is always a single non-terminal symbol that we've targeted for substitution. And then on the right, this is Gossett's language, is this sort of V thing. Okay, what is V? Answer anything so far. He writes that V is an element of sigma union delta star. Okay, but that's just a fancy way of saying, dude, take all the non-terminal symbols, so every element of your alphabet, all the terminal symbols, so in other words, literally every single character under consideration, put them all together in one big set, and then the star of that set is just all possible strings, the infinite number of strings which you can create from that. So in other words, this is really like sort of saying nothing. V is some mix of terminal and non-terminal symbols. And now I'm going to describe in 4 rules what properties this string on the right must have. In other words, I'm going to, what makes a grammar regular is what the right-hand side of the production rule is allowed to look like. Okay, and I think Gossett's presentation of this is extremely difficult to follow, so I've rearranged the rules in what I think is a more coherent order, and I will explain them. Okay, rule 1. V, in other words, the right-hand side of the production rule, can contain at most one non-terminal symbol. V can contain at most one non-terminal symbol. I'll just write non-terminal. Okay. In other words, whatever you're going to be doing over here on the right-hand side of your production rule, you can't have ever more than one non-terminal symbol over there. Okay, so for example, I could have a rule like big B. Oh, and it is standard, as you may have already sort of seen, it is standard to differentiate terminal symbols from non-terminal symbols by using uppercase letters for non-terminal symbols. These are the theoretical devices that we've created. And to use lowercase letters for the characters of the alphabet, the terminal symbols, the elements of the target language. Okay, so one rule might go like this. B goes to BB. That is an example of a valid rule that respects, a valid production rule which respects rule 1. So I'll put a little like smiley face there or something. Okay, because there's just one terminal symbol over there. So what's not allowed is to replace B with, say, 2 terminal symbols, and they are to be distinguished by the fact that they're uppercase. So that is not allowed. And another example of something that's allowed is to have no non-terminal symbols. So as we've seen, you eventually have to sort of make all like words from your alphabet. So you eventually need to sort of finish, the grammar needs to finish generating the string, and so in the end we convert all of the non-terminals into terminals. So you want to maybe have some rules where there are no non-terminals at all. Notice that rule 1 says that there are at most 1 non-terminal. You can have no non-terminals. So that's fine. So just to give one more example of something that's not allowed, you can't have like this, right? So once again, this is okay because there are no non-terminals. This is not okay because there are 2 non-terminals. Okay, good. That's rule 1. Rule 2, V must contain at least 1 terminal symbol. Okay. V must contain at least 1 terminal symbol. Okay, what does that mean? That means that in each of your rules, you have to have at least 1, well, I'll just show you some examples. What's one example is you could have some rule that went like B to AB, for example. That would be fine because there is a terminal symbol here. Another thing that you might do is just have B go to just A. We've seen that already. There is a non-terminal, a terminal symbol on the right. There has to be at least 1. That's what Rule 2 is saying. Let's not forget also that we may have rules of the form just lambda because we build into our sort of definition of grammar that regardless of the alphabet, the empty string is always a terminal symbol. Because we sort of need the expressive power of that empty string to say that a terminal symbol might just stop. Okay, so these are 3 examples of production rules which respect Rule 2. So of course, what's an example of a? Oh, okay, and there's even one more. So I got another one that's okay according to Gossett. B goes to like A, B, C. So notice that he says that V must contain at least 1 terminal symbol, which seems to suggest that we're allowed to have more than 1 terminal symbol. And this particular production rule replaces a non-terminal B with 2 terminals and a non-terminal. That is okay according to Gossett, but not okay according to some other authors. I'll say a little bit more about that later. But finally, what's not allowed is to replace B with like just a non-terminal. And so this gets a sad face. This violates Rule 2. Okay, and observant people will note that the grammar that we used to produce that fragment of English from the beginning did frequently violate this rule, and in fact, therefore, that is not a regular grammar. Okay. Whew. Rules 1 and 2 together say, in some kind of deep level, that with each substitution, so at each stage of the generation of the string, we are always making some kind of progress. That is to say, since I always insist on there being one terminal symbol on the right-hand side, then what that sort of you can interpret that as meaning that the terminal symbols are the characters of our target language. In other words, we produce at least one character of our string, of our word, per step in the generation of that string. So some progress, you can sort of watch the string being created, whereas in an example of a grammar which is not regular, such as the one that we were using to analyze that fragment of English, you will notice that sometimes many stages in the generation were consumed with sort of theoretical processes only, in which we were replacing terminals, non-terminals with other non-terminals, but not actually making any progress, seemingly, in creating our sentence. In a regular grammar, that can happen. You're making at least some of your sentence or your word per step. But also, because of Rule 1, which says that we can't have more than one non-terminal, you should think of the non-terminal symbols as being the symbols from which we will continue to generate like more stuff. And so what this is kind of saying is that if there's at most one non-terminal, it means that this, the sort of parse tree for this string generated by a regular grammar is going to be only branching kind of in one direction at any given time. We do not have, we cannot have a rule, like say over here, in which there are now sort of two non-terminal symbols from which further branchings can happen. And so this is a quite restrictive kind of grammar. Okay, and Rule 3 is also important. What Rule 3 says, if there is a non-terminal symbol, then it has to be on the right. Okay, so if V, still referring to the right-hand side of these production rules, contains a non-terminal symbol, contains a non-terminal, I'll just keep calling them non-terminals, non-terminal. If V contains a non-terminal, it must be the rightmost symbol. It must be the rightmost symbol. Okay, and okay, let's just see some quick examples of this. It means that you can do things like B goes to AB, but you can't do things like B goes to BA. And so, one second, this is good, but this isn't. And, okay, some people will call this a right branching regular grammar or something like that. What this kind of means, what the Rule 3 means is that, yeah, the parse tree, if you can imagine the parse tree associated with this, it's always going to be branching in one direction. In other words, we are sort of always going to be, not only are we going to be making at least some of our string at every single stage, but the, I think I have something more to say about this later, but well, okay, I'll hold off on that for a second. And okay, Rule 4, which is such a gossip, is so difficult to understand what he's talking about, but you can think of Rule 4 as saying, don't try to break Rule 2, and don't try to break Rule 2. Rule 2 says that you have to contain at least one terminal symbol, but lambda is a terminal symbol. And so you might think that I can, hey, aren't I allowed to have lambdas? I am allowed to have a rule that looks like this. But if lambda is a terminal symbol, and I have to have at least one terminal symbol, that's what Rule 2 says, then what's stopping me from doing like lambda c or something like that? Or b goes to c lambda. I think you should agree that that violates the spirit of Rule 2, because even though you have a terminal symbol on the right-hand side, it's the terminal symbol for the empty string. And so this rule now states, I forgot to write it down, if the only terminal symbol is lambda, so if the only terminal symbol is lambda, then there can be no terminal symbol. Sorry, there can be no non-terminal symbol. Non-terminal symbol. In other words, dude, if the only, well, there it is, right? If the only terminal symbol on the entire right-hand side is lambda, then, in fact, that needs to be the entire right-hand side, needs to be just lambda. You can't try to break Rule 2 by squeezing in a terminal, a non-terminal with sort of no terminal symbol by trying to, okay, I think that's good. Okay, so, good. Moving along, let's look at an example. I think we have seen this example already. Yeah, this is just our example from the previous video. Our example was, but now we're going to do it sort of formally. Let G be the grammar, which is sigma, delta, s, and pi. And now I will introduce sort of each of these elements. Formally, I say that sigma is ABC. Delta is SB. I don't think I used this terminology, delta, when I did this before. And pi, the set of production rules, are as follows. This is just the old system, right? S goes to AB, and B goes to BB. And B goes to C. Wait, I think, man, my brain is fried, but I think, yeah, this is exactly the example we did previously. Okay, good. Woo! Now just using this additional notation. We can observe that this grammar, I did not say this at the time because I hadn't defined regular grammar yet, but this grammar from the previous video is in fact regular. Because, well, basically we can just go right to the rules and we can see that every rule has a non-terminal symbol on the left, and on the right-hand side there is always at most one non-terminal, and there is always at least one terminal. Woo! I will mention one more thing, which is with very long, complicated grammars, it becomes annoying to write things out like this. So there's this notation, which is that if you have sort of two options for the terminal, for the non-terminal symbol B, then we can write them using this pipe thing. So B, pipe C. Think of that as an OR symbol. This is just another symbol of the grammars, which enable us to just express this a little bit more succinctly. Okay, and now to explore this grammar, let's do a derivation. I think I did this exact thing already, but just to introduce some more notation, let S be replaced with AB, which is then replaced with, following this rule, a BB, which is then replaced with a BBB, and finally a BBC. Okay, I need a bigger whiteboard. Woo. Okay, so this is a this is what's called a derivation. So this entire thing, let's switch to a different color. This entire thing is called a derivation. A derivation. It's just a string of application. It's a string of strings which begins with the start symbol and which ends with a string composed of characters from from sigma, each of which follows from the previous by an application of a production rule. And if some string can be achieved from another string by an application of one of those deductive rules, then we say that it is directly derivable. So directly derivable. And so we would say a, b, big B is directly derivable from a little b. And of course, if we can make the entire string a, b, b, c starting from the start symbol, then we say that S is, and this is now a new notation, we put a star on top here, and we get a, b, b, c. Now we just say derivable. So, okay, this says derivable is another piece of vocab. A, B, B, C is derivable from the start symbol by following a finite sequence of substitutions. Okay, a little bit more. The language generated by G, so the language generated by G is the set of all words that can be derived from S. That can be derived from S in G. So just kind of duh. Start with S and follow all possible rules, and what you will get is a set of strings. This set will surely be an infinite set, and so that we call the language. So the language of some grammar is simply the set of all strings W drawn from sigma star such that there exists a derivation from the start symbol to that string. It's fairly intuitive. Okay, and finally, all right, I don't want to write this because I'm running out of space. Finally, we say that a certain language is regular if and only if there is a regular grammar which generates it. So, different people define this differently, but for Gossett, he is going to define a regular language. These are the things that we're studying right now. A language is regular if there exists a regular grammar that generates that language. Okay. Whew. Just a quick note, which I'm going to sort of squeeze in here to this place. Let's just represent this derivation that we did here with a parse tree. And so I start with my, I was alluding to this earlier, but I think it's nicer if we just kind of look at it, right? So similar to before, here's A, B, B, C, which is the string we are trying to generate. And how did we do it? Well, we replaced A with sort of A, B, and we replaced B with BB, so sh, and we replaced that second big B with little b, B. How did I mess this up? Arg. 1 second. B, 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 and I still messed it up. C. Just things were just bigger than I thought. So it looks like that. Yeah, and that's just right. Okay, good. Okay, so this tree represents the sort of the structure of the string A, B, B, C that we generated with this grammar. And I think for a language, well, I'll just leave it like that. Okay, and what I was saying earlier is that you can sort of see that the language, when the grammar is regular, that this is sort of generated like in a left to right style. So you can think of the non-terminal symbol at any given time as being like a kind of cursor. And the cursor is that's the only live symbol which has any kind of generative power. After all, once we've replaced S with AB, A is now not going to do anything anymore. It's a terminal symbol. It's the meaning of terminal. We've sort of stopped. But the non-terminal symbol is still live. It has literally not terminated yet. And so the only room for this word to grow in length is going to be from this non-terminal symbol. And sort of all these rules conspire together to say that because there can only be one terminal symbol on the right-hand side, that's rule 2, it means that there's only ever one cursor at any given time. And because by rule 3, the non-terminal symbol must be on the right edge, then it means that the tree is always branching rightward. And okay, and so at any given time, there's only one live spot, and then when we're done, we're done. Okay, so this is a very simple category of languages, regular languages, and regular grammars are also very simple, yet actually pretty powerful. Good. And I'll say one more time that because the trees that we drew, the parse tree that we drew for our linguistic fragment from the first video did not have this kind of structure, and that's because that was not a regular grammar. Okay, let's look at another example. And for this purpose, I think the smart thing to do is to erase this, but not all of that. Let's see if that's a good idea. So here's just another kind of simple example. Okay, now I give you a sigma which has just, so just A and B, and delta is S and X, and here are the rules. The rules are S goes to either lambda or ABX, and and X goes to ABX or lambda. Okay, so let's try to understand what this grammar is doing, and that'll be great. Okay, what is this grammar doing? Well, it has some kind of start symbol, and one option is that it just ends immediately. So in fact, the empty string is a string of this language. But if it doesn't end immediately, then we get a new string, which is ABX. Okay, so it seems like our word is going to either be empty or it's going to begin with AB. And then once I'm on X, what does X do? Well, X at any given point either just ends or it just makes another AB. So it seems as if this grammar is just going to generate AB, 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 AB. And in fact, that's just true. Good. So I'll just say that right now, that the language, if this grammar is called G, then the language of G in this case is going to be lambda, AB, 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 etc. Okay. Can I sort of convince you of this? I think I can. I'm going to make a tree. I don't know what it's called. I'm sure there's a name for it. It's not a parse tree. It's instead a kind of a decision tree that I think is helpful when learning how to do this. So just let's imagine, especially when there's any kind of, well, in fact, it's only when there are it's when there are sort of it's when there's more than one option for a given non-terminal symbol that I have branching. And here there certainly some branching, so we want to consider all of those options. So, well, the first thing that can happen is I could just follow that rule, and then the string, then the thing just ends. So the empty string is a string of language, as I said. But the other option is that we follow the other rule and we get ABX. Well, then there's the option in which I follow this rule for X, in which case I end with the string AB, and here I end with and the alternative is that I follow this rule and I replace that X with another ABX. Okay, I think you sort of get this now. Then, of course, what can I do with this X? I have two options. I can replace it with lambda, in which case the entire string just becomes A, B, A, B, or I can replace it with, I can follow this first rule, in which case this becomes A, B, A, B, A, B, X, and then this is just going to continue. Okay, so in this case, we have a tree for which the leaves of the tree are valid words generated by this grammar. And I think this is helpful when you are trying to figure out what a certain grammar does, or if you are attempting to write a grammar, as you will do on the homework, to generate a certain language and you want to check whether you've done it correctly, which is kind of the same thing. Okay, sort of theoretical thing, note, some authors, and you might also, I've had some students in some years who really don't like the way Gossett does this, and I should say that almost everything we've learned so far this week, okay, this unit just started, is something that you may have learned about from ACSL or something like that. And so some people have some experience with regular grammars, perhaps, and regular languages from some prior course or some other experience. And so you may see a slightly different definition out there. And the slightly different definition disagrees that you are allowed to have, it's right here. I'll put a little green star here. It's strings like this, which some authors feel should not be allowed. Rules like this, rather, which some authors feel should not be allowed. And in some ways, things are almost kind of better if you take this kind of hardline approach. The hardline approach is to only allow there to be one terminal symbol per production rule. Gossett has a rule that says there has to be at least one. If we also say that there's at most one, then it's somehow more elegant because we can insist on there being exactly one terminal symbol per right-hand side of any production rule. What am I talking about? Well, note that two of the rules above, one of them says that S goes to A, B, X. Another one says that X goes to A, B, X. In the world of these other authors, these would be not allowed and would need to be replaced and amended. But we can kind of always do that by introducing a new non-terminal symbol which captures the idea that we're like halfway towards writing AB. So instead of SABX, we have a rule that says, so this is the other option, S goes to AR, say. And we can also have a rule that X goes to AR. But what is R? Well, R just picks up where this rule sort of left off, and R is just BX. And, okay, these three rules over here on the right are certainly follow all of Gossett's rules for the production rules of a regular grammar, but they also have exactly one terminal symbol per rule on the right-hand side, and I think you've seen that we've lost no sort of power, right? So we don't